when you look at the screen at the moment, you can see a schematic. On the left-hand side shows us the designs or schematic for the conventional MIs. On the right-hand side shows the concept put forward by the researchers at Cambridge. That was to have an inner wall, a second or dual or double wall design, where this dual wall or the inner wall material was made from a suitable material that would stop or reduce migration of materials from the outer wall to the conductors. What I'd like to do now is talk about, show you a set of graphics or animation that shows the concept of what the researchers found, is that under conventional conditions in high temperature, contamination was caused on the conductors from migration from outer sheathing itself. This caused a change in the metallurgy, which caused a change in EMF output, which was the source of the drift. With this new low drift design put forward by Cambridge University researchers, this inner wall would stop or reduce this drift, and in turn stop or reduce the metallurgical contamination of the conductors, and therefore stop or change the drift. So what I'd like to do now is show you a series of test data conducted on this new low drift cable in comparison with the conventional cables that are used in industry today. This first test was conducted at the CCPI Europe laboratories, and it was actually conducted on 3mm diameter Inconel sheathed Type K conventional MIs against the new low drift dual wall counterpart. The actual temperature conditions of the test were actually cycling conditions, and one cycle is shown on the slide. It starts at 400 degrees C, goes to 650, 850, 1050 and 1250 degrees C, holding at each temperature for 1 hour, and then cooling down to 400 degrees C. This being one cycle, this taking some 390 minutes per cycle. The actual thermocouples are subject to 91 of these cycles, or 24.4 days of continuous high temperature thermal cycling. The results we're going to look at are going to show us in chart form the change in EMF output in degrees C over those 91 cycles for the respective test thermocouples. So the chart you're looking at down the y-axis is the change in EMF output over the 91 cycles in degrees C, across the x-axis at the temperature points of calibration during the test. So first of all, let's look at the data from the conventional thermocouples. Two units were tested. First one in blue shows us the change over the 91 cycles was between 12 and 11 degrees C. The second one in red shows us it was slightly larger, between 15 and 17 degrees C over the 91 cycles. Now in comparison, under the exact same conditions, let's have a look at the performance of the new low drift design. Again, two thermocouples were tested. Both thermocouples over the complete temperature range of testing over the 91 cycles showed less than 3 degrees C movement. As predicted by the researchers at Cambridge, somewhere between a 73 and an 83% reduction in drift was observed when the new low drift thermocouple designs were compared against the conventional designs being used in industry today. This next sequence of testing was conducted at extremely high temperature of 1320 degrees C, above 2400 Fahrenheit. A temperature would not normally recommend Type K or Type N thermocouples to be used at. The actual test conducted was for some 52 hours or 2 days of operation, and the thermocouples that were tested were the same as the previous set of data, i.e. 3mm diameter Type Inconel sheath conventional against their 1/8 diameter dual wall low drift counterpart. Results we're going to look at, again in chart form, are going to show us the correction value or changes in correction value in degrees C at the test temperature of 1320 for the respective test thermocouples. So in this instance, the chart showing you the change or change in correction in degrees C down your y-axis, and the time in temperature in hours, the time in hours across your x-axis. So first of all, let's look at the performance of the conventional thermocouple. As we would have expected, a continuous drift was observed, an increase in the correction value, a lowering of the EMF output value, starting at some 3.5 degrees, moving to some nominal 15 degrees, showing a nominal 12 degrees C shift over the 52 hours of operation. Actually quite a good performance for a 3mm diameter Type K thermocouple. Now let's look at the performance of the new low drift design under the same conditions. Well, you can observe a significant difference. Again, starting off at some 3.5 degrees, but finishing at less than 5.5 degrees C correction value, less than 2 degrees C nominal movement, or, as predicted by the team of researchers at Cambridge, an 83% reduction in drift characteristics was observed. Really, from this data, from significantly large quantities of data from tests carried out at Cambridge and CCPI, the researchers at Cambridge were able to establish and predict that the drift levels of this new design were reduced between 80 and 90% when compared to conventional designs